In this video, we're going to discuss the principle of minimum potential energy at equilibrium. The schematics shown here represent three types of static equilibrium. In the first type, we have a small cylinder inside a larger cylinder. When you take the sum of forces equals 0, you have the weight of the small cylinder and the reaction, and so the sum of the forces are equal to 0. If the small cylinder is perturbed, then it will vibrate around its equilibrium position and then it will go back to its original position, and so this equilibrium is considered a stable equilibrium. In the second shape, we have a cylinder on a flat surface. If we perturb the position of the small cylinder, then it will move and will stay in the new position, and therefore this type of equilibrium is called neutral equilibrium. In the third schematic, we have a small cylinder on top of a larger cylinder. When the small cylinder is sitting on top, if we take the sum of forces, we get a reaction and the weight of the cylinder. The sum of forces are equal to 0. However, if the position of the small cylinder is perturbed, the equilibrium is lost, and so this schematic represents unstable equilibrium. The concept of potential energy of a system allows us to examine whether an equilibrium position is stable or not. As we defined it previously, the potential energy of system is equal to the internal stored elastic energy minus the work done by the external forces. For a 3D solid structure, the potential energy of the system is defined as the internal energy minus the work done by the external forces. If it's a linear elastic structure, then the internal energy is equal to the sum of each component of the stress multiplied by the corresponding component of the strain divided by 2. And the work done by the external forces is the work done by the body forces vector rho b through a displacement u, and the work done by the external forces acting on the surface, taking the dot product with the displacement u. For an Euler-Bernoulli beam, the potential energy of the system is defined as the internal energy, which in this case is EI divided by 2 multiplied by the second derivative of y with respect to x1 squared, all squared, minus the work done by the external forces, and the external forces acting on the beam are the distributed load Q, and so the work done is Q multiplied by y integrated over the length, minus any force multiplied by the corresponding displacement, and any moment multiplied by the corresponding rotation. For a beam under axial loading, the potential energy of the system is defined as the internal energy, which is EA over 2 multiplied by the strain squared, and the strain is du1 by dx1. And this is of course integrated over the length. This is the total energy stored in the beam, minus the distributed load P multiplied by the horizontal displacement u, and this is integrated over the length, minus each component of an external force multiplied by the corresponding component of the horizontal displacement. The potential energy of the system allows us to differentiate between the different types of equilibrium. At stable equilibrium, the potential energy of the system is minimum. If it's an unstable equilibrium, then the potential energy of the system is maximum. In neutral equilibrium, the potential energy is constant. Of course, no equilibrium is achieved if the potential energy is neither maximum nor minimum, nor constant. We are going to examine this principle using an example. The shown rod supports a weight of 900 Newton in the middle. It's pinned at point A, so it can rotate around point A, but this point cannot move horizontally or vertically. It's also subjected to a moment of value 140 Newton meter at point A. It has a spring, and this spring is attached through a roller. The stiffness of the spring is 750 Newton per meter. We would like to find the possible equilibrium positions described by the angle theta, and we want to know whether they are stable or not. The unstretched length of this spring is 0.6 meters. To find the equilibrium positions, we can just use Newton's equations of equilibrium. Sum of forces equal 0, and sum of moments equal 0. If we sum the moments around A, and if we consider the clockwise direction as negative, then we have the sum of moments around A. First, I have negative 140 Newton meter, and then this weight, 900 Newton, multiplied by the horizontal distance, and the horizontal distance is equal to 1 cosine theta. The force in the spring is equal to 750 multiplied by the stretch in the spring, and the stretch in the spring is equal to this vertical distance, and this vertical distance is equal to 2 sine theta. So this is the force in the spring, multiplied by the distance, and the distance is equal to the horizontal distance, this distance from this point to this point, is equal to 2 cosine theta. And so the equation becomes negative 140 and negative 900 cosine theta plus 3000 sine theta cosine theta equals 0. And so to find equilibrium, we want to find theta that satisfies this equation. Using a solver, a mathematical solver, we are able to see that there are 4 possible angles theta that would satisfy this equation. Theta is equal 19.6 degrees, 87.27 degrees, 164.61 degrees to 168.53 degrees. And it's not obvious which of these are stable equilibrium and which are not stable equilibrium. And so we're going to utilize the principle of minimum potential energy to identify the difference between these types of equilibrium. The potential energy of the system is equal to the internal energy, which is the energy stored in the spring, minus the work done by the external loads. The internal energy is equal to half kx squared. And so k is equal to 750, half, and the x, which is this distance, is equal to 2 sine theta. The work done by the external forces, the first force is the 900. 900, the work done by this force through this displacement is equal to 900 multiplied by the displacement, and this displacement is equal to sine theta, 1 sine theta. And finally, we have a moment here, so the moment multiplied by the rotation gives me the work done, so 140 multiplied by theta. At equilibrium, partial potential energy by partial theta is equal to 0. So this equation is what gives me the equilibrium. And if you notice, partial potential energy by partial theta gives me an equation, and I set this equation equal to 0. This is exactly the equilibrium equation. So this is exactly equilibrium equation. And so the solution to this is the same. And so I get the 4 possible angles that I obtained before. To identify the type of equilibrium associated with each angle, I will take the second derivative of the potential energy with respect to theta. So I get this equation. And then for each equilibrium, I evaluate the second derivative of the potential energy. When theta is equal to theta 1, I get a positive number. When theta is equal to theta 2, I get a negative number. When theta is equal to theta 3, another negative number. When theta is equal to theta 4, I get another negative number. Which means that the only stable equilibrium is the first equilibrium when theta is equal to 19.6 degrees. The other ones are unstable equilibrium. Maybe instantaneously the rod can be stable, but the moment that equilibrium is perturbed, equilibrium is lost. And so the stable equilibrium is the one associated with theta 1 equal 19.6 degrees.